In this segment, we're going to be looking at the powerful applications of exponential equations or exponential functions. We've already looked at some of those in a previous session in which we were looking at exponential growth using compound interest in money applications. There's an old statement that everything old is new again. Well, from financial applications, if you recall, when we did continuous compounding, we got what some people called the PERT formula. The amount of money that you have at any given time t is equal to P, which was our principal, the amount of money we started with, times e to the RT, where R was the interest rate that we were given. Well, for growth and decay models, we have a more common version of the formula, which is equal to A equals A sub 0 e to the KT. Now, I've color-coded this on the PowerPoint so we can see that these are really the same formulas, just different letters. And the letters really don't make any difference as long as we keep up with those. So note with our formulas that P in our first formula is the same thing as A sub 0. And if you'll recall in those financial applications, P was the principal. The principal is the initial amount of money that you start with. Well, in our growth and decay models, A sub 0 is the initial amount of, say, population or the initial amount of radioactive decay material that we will be dealing with. And then we also notice that R in the PERT formula is now K in our exponential growth and decay formulas. And remember that R stood for the interest rate. It's how fast our money is growing. Well, if we look at K, that's going to be how fast a population is growing in case of population growth, or how fast a material is decaying in the case of radioactive decay. So let's take a look at how this works out in growth and decay. Now, as we do that, consider the graphs of f of x equals e to the x, that's our blue graph, and g of x equals e to the negative x. And what I'm concentrating here on is a positive exponent versus a negative exponent. When our exponent is positive, we're on the blue graph. And as we go from left to right, our function is increasing. And so we have growth. But when our exponent is negative, we're on the orange graph. And as we go from left to right, in other words, as x is getting larger, our function is decreasing. It's getting smaller. And so consequently then, in our formula that we're going to be looking at, the amount of material or population at any given time is equal to the initial E times e to the KT. When K is positive, we're going to have growth. But when K is negative, it'll be like this orange graph. We'll be having decay in our problems. Okay, so let's look at some examples and you determine whether we have growth or decay. So in 5 different examples here, our first one, A equals 900 e to the negative 0.25 t. And in this case, remember we're looking at K, and K is negative 0.25, so K is less than 0. Therefore, we have decay. But not only do we know we have decay, the negative 0.25 is our rate of decay. So this material would be decreasing at a rate of 25% each time period. Okay, in our second one, K is a positive number. And so since K equals 0.075, then we have 7.5% growth. In the third example, you now are getting used to this, I hope. K is 0.25, and so we have a positive K, which means we have 25% growth. And in the last, or next to the last example, K once again is positive. 0.0625 translates into 6.25% growth. And finally, in the last one, we have negative 0.25 as K. Notice I've ignored completely what we start with. That's why I threw these last two examples in. I don't care whether our initial amount's positive or negative. We're simply looking at K to determine whether we have growth or decay. And in this last one, K is negative 0.25, which means we have 25% decay. Now let's look at some examples. One very useful part of exponential equations is growth of a population. We're going to look at the growth of the population of the United States from 1970 to 2000. In this case, we want to start with the facts that in 1970, the population of the United States was 203.3 million. In 2000, it was 281.4 million. We would assume that those numbers come from the U.S. Census Bureau, which takes the census every 10 years. So in other words, these are reliable numbers that we can count on. Now what we want to do is find a model for the U.S. population in years after 1970. Because if we can find our model, then we can use that model to estimate the population in any given year. We'll do that in just a minute in 2011. Or we can find when our population reaches certain key points, which would be, say, 300 million or 400 million in population. So let's take a look at how we're going to do that. Now, if we want a model, our model is going to be of the form A, the population at any given time, equals our initial population times E to the KT. Well, we need to identify what A sub 0 and what K are in this case. Now, it's important to note that in our given information, if we let T equal 0 in 1970, we have 2 points given. One is T is 0 and the amount of the population is 203.3 million. The other is in 2000, T is going to be 30 and the population was 281.4 million people. Now let's see how we use all of these facts and put them together to come up with our model. Okay, as we said earlier, we need to find A sub 0 first. Well, and then find K. To find A sub 0, since T is 0 in 1970, we can put 203.3 from our point up here in place of A, and we can put 0 in place of T. And now, if we do that, we will get that 203.3 equals A sub 0, E, K times 0 is 0. But remember, E to the 0 is simply 1. And so that means that our initial population, which is not a surprise if you think about it, is considered to be 203.3 million because we let time be 0 in 1970. So the initial population, A sub 0, is going to be 203.3 million. Now, how can we find K? Well, we're going to use our other point that we identified, 30, 281.4, to help us find K. In 2000, T is 30, we said, and A equals 281.4. So using that in our equation, 281.4 is equal to 203.3 e to the 30k, where we've put 281.4 in place of A and 30 in place of t. Now we've got an exponential equation, and it involves k, which is what we want to solve for in this case. And if you'll recall from when we solved exponential equations, we first want to isolate the expression that involves k, and that is e to the 30k. So we divide both sides of our equation by 203.3, and that gives us a number, 281.4 divided by 203.3, and that is going to equal e to the 30k. But how did we get that k out of the exponent? If you recall, we did that by undoing exponents, which is taking the natural log of both sides. And so at this point, we get the natural log of our expression on the left side equals the natural log of e to the 30k. But if you recall, the natural log of e to any exponent is simply the exponent. So the natural log of e to the 30k becomes simply 30k. And now we can easily solve for k by dividing both sides by 30, or multiplying both sides by 1 over 30. Now, let's put this in our calculator so that you can see how I came up with the number 0.0108 before we talk about what that means. So let's look at this on our TI-84 calculator. Now remember, we want to take 1/30th of the natural log of 281 divided by 203.3. So on our calculator, we're going to start with parentheses 1 divided by 30 to get 1/30th, and then close the parentheses, times the natural log, and this is where we need to be careful. It's the natural log of the quotient, which means we're going to take the natural log of 281.4 divided by 203.3, and then close our parentheses. And when we do that, we get 0.011 or 0.0108, depending on how many places after the decimal. Now let's go back and look at what that means in our particular example. Well, what we have found out is that we now have a model for the population of the United States. The amount at any given time, t, will equal 203.3 e to the 0.0108. I went 4 places after the decimal, t. And so that means that k, which is 0.0108, means that our growth rate during that time was approximately 1.08% per year from 1970 to 2000. Now, how can that information help us to solve other problems? Let's continue this problem on the next screen. On the next screen, we're going to use our model, A equals 203.3 million e to the 0.0108t, to estimate the population of the United States in the year 2011. Now remember, t equals 0 in 1970. So if t is 0 in 1970, 2011 will equal 41. And so consequently, all we need to do at this point is put 41 in place of t up here in our model, and put that in our calculators, and we'll find that the estimated population for the United States in 2011, according to our model, is 316.6 million people. Well, we can use that also, as we said earlier, to find some significant times when our population has reached significant figures. In this case, we'll be looking at when will or did the population of the United States first reach 300 million? Well, we know it has to be before 2011. But how far before 2011 was it? Well, in this case, you note that we are given an amount. This is going to be A. When indicates that we're looking for a time. So in our equation, we will be putting 300 million in place of A. Let's do that. Okay, and we can solve for T. And as you recognize right here, once again, hopefully you learned your lesson on solving exponential equations very well, because now we have an exponential equation, because T, what we're looking for, is in the exponent. Well, we need to isolate the expression that involves our exponent, and that expression is e to the 0.0108t. So that means I need to get rid of this 203.3. And I will do that since I'm multiplying by dividing both sides by 203.3. And in that case, we get 300 over 203.3 is e to the 0.0108t. But I can get t out of our exponent if I'll take the natural log of both sides. But remember, the natural log of e to any power is simply the power. Hence, this equation is what we will have. And to solve for t, we simply divide by 0.0108 or multiply by 1 over 0.0108. And when you put that in the calculator like we did before a few minutes ago, you will get 36.02. Well, 36.02 means that t equals 36.02. That's 36.02 years after 1970. And when we add those, we'll get sometime in 2006, according to our model, the population of the United States went from, surpassed 300 million. And that actually is very close to what happened in the United States at that time. Okay, now let's look at a decay. We've looked at growth from population. Now we're going to look at a popular dating technique, which is called carbon-14. Carbon-14 has a half-life of 5,715 years, which means if I had 100 grams of carbon-14 today, 5,715 years from now, I'll have half of that material, or 50 grams. And in another 5,715 years, I would have half of that 50, which would be 25 grams, and so on. So let's suppose that a charred piece of wood is determined to have 90% of the carbon-14 that a freshly cut piece of wood has. We need to estimate the age of the charred piece of wood. Well, in this case, we need to look at our model first of all, and remember the model is the amount at any given time equals the initial amount, e to the kt. Now, since we're decaying, we're going to be expecting k to be a negative number. That's just a check that's in the back of our minds as we work this problem. Notice we don't know what the initial amount is, but that's not going to be important here, as you'll see in just a moment. What is important is we need to find the rate of decay. And so to find k, we remember that the half-life is 5,715 years after t equals 0. So the amount at that point in time will be half of what we started with. So A equals A sub 0 over 2, half of the initial amount, will equal the initial amount times e to 5,715k. Now we can once again take this logarithmic, or this rather exponential equation, and solve it for k, just like we've been doing time and time again. So the first thing we'll do is take this equation and divide both sides by a sub 0. And notice when we do that, a sub 0 falls out of the problem, and we have 1/2 or 0.5 equals e to the 5,715k. By taking the natural log of both sides, the natural log of 0.5 will now simply be our exponent, 5,715k. And now it's a matter to solve for k, simply divide by 5,715. And when I divide the natural log of 0.5, be sure and close the parentheses there if you're putting that in your calculator, by 5,715, I get approximately negative 0.00012, which means that the rate of decay for carbon-14 is going to be 0.012% per year. So that piece of wood is losing 0.012% of its amount each year. Okay, now we can get the wood's age at that point by saying, all right, A, the amount, equals 0.9 times A sub 0. Remember, we're estimated to have 90% of the carbon-14 left. So the amount today is equal to 90% of the amount that it started with. So plugging that in our new model now, we get 0.9 A sub 0 equals A sub 0 e to the negative 0.00012t. Divide both sides by A sub 0. Once again, notice A sub 0 falls out. We're left with the natural log of 0.9 equals negative 0.0012t. And at that point, divide by negative 0.00012, and we get t is 878 years old in our carbon-14 dating. So in this lesson, we have seen that we can use exponential expressions, in particular A equals A sub 0 e to the kt, to solve both growth and decay models.